This is the second part of lecture 13. Now we are going to talk about PID control. The PID control modes offer continuous process adjustment if the equipment can physically provide it. Some of the modes can drive the Azure ET to 0 in response to step changes in the set point or a load. And final control device must be continuously adjustable. And there are 5 options of PID control: proportional control, integral control, proportional integral control, proportional derivative control, and finally the famous PID control. Before we jump into the control modes, let's first define the steady-state process adjustment, PS. PS is the process adjustment setting in Laplace domain P(S) at steady states, when there is no difference between the set point and the measured process output, which gives ES to be 0. Now we start to talk about proportional control, which is the first PID-related control mode. The time domain relation for proportional control between the control output and the Azure is shown in the following equation: PT equals KPET plus PS, where PT is the time-dependent process adjustment, KP is the proportional gain, ET is the time-dependent Azure, and PS is the steady-state process adjustment, or setting. The transfer function for proportional control in the Laplace domain is PS over ES equals KP, where again KP is the proportional gain. The lower right gives the block diagram for proportional control, which is quite straightforward. Some proportional control observations are: small Azure produces a small process adjustment and vice versa, which is large Azure produces a large process adjustment. Proportional control handles changes in Azure well, but it does not handle constant Azure well, which means it has offsets. And large proportional gain, KP, reduces offset, but can produce potential oscillations. Next, integral control. The time domain relation for integral control between the control output and the Azure is shown in this equation: PT equals Ki times integral ET dt plus PS, where PT is the time-dependent process adjustment, Ki is the integral gain, which is rarely used in real-world effect, and ET to be the time-dependent Azure, and PS again be the steady-state process adjustment or setting. The transfer function or proportional control in the Laplace domain is PS over ES equals Ki over S, where Ki is usually set as Kp over tau I, where tau I is the integral time and Kp is the proportional gain from proportional control. Observations of integral controls are: if process adjustment does not have an effect on the process output, then process adjustment PT continues to increase. Usually used to eliminate proportional control offsets, therefore sometimes integral control is also called reset. And if integral control is used alone, it produces oscillations around the set point. For proportional plus integral control, the time domain function and the transfer function are by adding control functions of proportional and integral controls, which gives pt equals kp times et, which is the proportional control function, plus kp divided by tau I integral et dt, which is the integral control function time domain relation, plus ps, which is the steady state process adjustment or setting. The transfer function is ps over es equals kp times 1 plus 1 over tau I times s. And the block diagram for proportional plus integral control is shown in the lower left of this slide. So you see that proportional plus integral control is just the addition of proportional control and integral control. It's convenient, right? Next, let's talk about proportional plus derivative control. So from the name, we know that it's proportional and the derivative is instead of integral. That's why here in the time domain relation, we see pt equals kp times et plus kp times tau d and det divided by dt plus ps. So again, kp is the proportional gain and tau d is the derivative time. Et is the error, time-dependent error, and ps is the steady state process adjustment. So the transfer function based on pt is that ps divided by es equals kp times bracket 1 plus tau d plus s times s. And the block diagram for proportional plus derivative function is shown in the lower right part of this slide. So some facts about derivative control is that derivative control is never used alone. The process adjustment depends on the change rate in error. And derivative control gives a quick response to changes in error. Finally, we combine the three together to get the proportional plus integral plus derivative control, which is the famous PID control. The time domain function and the transfer function for PID control is by adding the three control functions together. Therefore, we get this PT form here with the three parts plus PS. The transfer function is PS over ES equals KP times 1, which is from the proportional control, plus 1 over tau IS, which is from integral control, and finally plus tau ds, which is from derivative control. And the block diagram is shown in the lower right of this slide. Therefore, we need to select our Kp, tau I, and tau d for a specific system setup. For example, the UAV system that we talked about in our last lab session. So the use of PID control has grown with the use of programmable controllers and more controllable devices that can have continuous adjustment. And PID control can provide very fast response and very tight control. In the end, we are going to solve an example problem, which is 14.1 in your textbook. In this example, you are asked to, in a proportional and derivative control system, to find PS, PT, and the values of P0, P0 plus, and P2, given the following values for Kp, tau I, tau D, and PS. Step change in Azure ET is set to 2 once the control system starts to run. So the solution for such a question can be found with the following several steps. First, write the transfer function for control, and then write the transfer function for Azure. Based on these, you can find your PS, and then you can invert it back to PT. And by using PT equation, you can find values of P0, P0 plus, and P2. So refer back to where we talk about the transfer function for PI control. We get the PS over ES equation, which is equal to Kp times 1 plus tau D times S. And then we can write the transfer function for Azure step change of magnitude 2, which the question or the problem already gave us. So we know that ES equals 2 over S. Based on ES and the PS over ES, we can now deduct what PS is, which we show it here. PS equals 2 over S Kp times 1 plus tau ds, which in the end give us 6 over S plus 8. So then the next step is to invert to find PT based on PS, which we get PT equals 6 plus 8 times delta t, which is an impulse function. So in the end, use PT equation, we can find the values of P0, P0 plus, and P2. At time 0, where there's no feedback input to the system yet, and we have only the steady state process adjustment. Therefore, P0 equals to PS, which is 1. When the system starts to work, we have P0 plus to be 8 times 6 times 8 times 6 plus 8 times delta 0 plus and plus 1, which gave us 6 plus 8 plus 1. And P2 to be 6 plus 1, because at time 2 we don't have any more pulse signal already. There are 2 more examples in textbook for your reference. So to summarize today's lecture, we learned closed-loop control systems, including 2-position control and PID control transfer functions and time domain control functions. If you have any questions, make sure you write them down in your notebook or in a blank paper so that you can bring it to class or lab and we can discuss. Okay, thank you. This is